You guys see my screen?
Yep.
So Joel, as we discussed, maybe towards the end, I know people leave, some people leave early. So I don't know if you want to announce the speaker for the next session in the beginning, or should we just keep it towards the end?
Sure, we can announce it at the beginning. Do you want to fast forward to that slide? And I'll first welcome everybody and introduce the speaker, which is Prateek Prasanna, who's a brilliant junior faculty who we were fortunate to recruit to biomedical informatics. And he's going to be giving I think, very, very interesting talk. We've been working together at Stony Brook on some of this work that he's been leading with his grad students. And this also actually connects very nicely to work at Midrick. So next slide, please. So every now and then, I think we should show progress in terms of the nuts and bolts of aggregating data. It's been a while, so there's 65 sites for released data in the N3C pipelines, 267 sites with DUAs executed, with almost 3 million COVID positive cases, which is obviously not good news in terms of the pandemic not winding up as quickly as many of us thought it might have. But certainly it's a remarkable data source. So in the talks the next week, you fast forward, Usman. Fire in the Tenant Model by Rahu Hamadri, Chris Polimas, and Scott Gordon. And the tenant model, I think, is going to become a really important thing going forward. And so I encourage people to attend that. And obviously fire is extremely important. And I think you've got another slide for the more distant future. So we've got a lineup over the next month and a half. RADX UP by Giselle Corby-Smith, and then N3C data quality manuscript, which has been a really important work led by Emily Pfaff. And let's see, I can't see the 15th, but the 15th will remain a mystery to me. Okay, anyway, I can't see who it is. Okay, so Prateek, okay. N3C cardiovascular disease team on the 15th, TBA. Okay, so with no further ado, Prateek, hand it over to you.
Okay, so let me go ahead and share my screen real quick. Okay, so let me know if you can see it. I guess you can. Okay, so good afternoon, everyone. I'll be talking about our work here at Stony Brook University, especially focusing around building image analysis and machine learning for discovering subtle COVID-19 visual features. So though we have done a lot of work on both CTs and radiographs, this presentation today will center mostly around our work on chest radiographs. So before we get into the details of what we have done so far, here's a quick snapshot of the general research team of a lab. So it lies at the intersection of machine learning and image analysis, wherein our focus is on biomarker discovery via different machine learning and multi-scale data fusion techniques. So heterogeneity, like you all know, lies at different length scales. Our group has been focusing on developing markers of imaging heterogeneity for different modalities, mostly focusing on MRIs, CTs, X-rays, and also fusing them with different kinds of heterogeneity markers that we get from digital pathology. So many of the tools that we develop are domain agnostic and are applicable across disease sites. And we have been using these tools to exploit subtle cues on imaging, which are otherwise not discernible to the human eye. So in this presentation, I'll be talking about a few of the different tools that we have developed and how these are applicable to COVID image analysis. So a huge shout out first to our team at Stony Brook University. We put together a huge group that amassed this huge data set of imaging data and also associated clinical data. And in fact, now we have contributed to one of the largest publicly available imaging data sets on TCIA. So I believe as part of the TCIA N3C collaboration, some of these will be linked to the available clinical data as well pretty soon. So in the TCIA, we have images of close to 1,300 patients. However, in our Stony Brook Data Commons, we have over 9,000 patients and 2,000 curated data elements, ranging from images, clinical notes, meds, lab data, demographics, and so on and so forth. So here are the three core pieces of work that we have been involved in so far. So first, I'll be talking about developing radiomics and deep learning pipelines to predict clinical outcomes in COVID-19. Second, I'll be talking about how we can leverage sequential imaging data to study COVID-19 progression on temporal chest radiographs. And finally, I'll talk about a new model that we have developed where we can disentangle the structure from the texture of images. And in a sense, we can generate hybrid images, which can lead to better outcome prediction. So these are some of our recent publications that have come out of our COVID-related work. So Radiomic Features is something that I'll talk about first. So the first project here is on outcome prediction using radiomics and deep learning on chest radiographs. So radiomic features, for those who are not aware, are subvisual yet quantitative features that we can compute from radiological images. And these are handcrafted imaging descriptors that can characterize both local and global heterogeneity in medical images. So, I mean, obviously, the first logical question here was, if you can develop a radiomic model to predict outcomes in COVID patients, how would it compare against a deep learning model? So we used both radiomics and deep learning to predict ventilation requirement and mortality on baseline chest X-ray scans. More importantly, we devised a deep learning model that could fuse clinical information with imaging information that actually resulted in better outcome prediction. Another core contribution of this work was, just give me a second. Yeah, so another core contribution of this work was developing a model that can remove obstacles from the images before feeding them to any machine learning algorithm. So like with most medical imaging applications, this also needed a lot of domain-specific pre-processing. So a lot of initial work that came out during the initial stages of the pandemic, machine learning models used to be given these images. And yes, the performance was really good, but when we, from an interpretability perspective, when we went in and looked at the salient regions or the class activation maps, we found that a lot of times the machine learning models were focusing their attention on regions outside the lung. Now that was obviously an error and probably something that resulted in overfitting. Now, what we did was the first model that we trained here, it could segment out the lung fields. And in addition to the lung fields, we also segmented out different artifacts such as wires and EKG leads and whatnot. So only after we segmented out these different regions, the regions inside the lung fields were given to our machine learning algorithm to learn different features. So that was the first domain-specific pre-processing that we did here. And the second pre-processing was histogram adjustment. Now, when we first got our data from Stony Brook University, the performance was, it was great. But then when we tried it out on data sets obtained from Rutgers, from Newark Beth Israel Medical Center, we found that the performance wasn't really that good. So what you see in the first row are examples of images taken from these two centers. So we can clearly see that the histogram distribution, once we had the histogram distribution of these images, it was pretty different from the ones from our cohort. So we did a histogram adjustment, and after histogram adjusting these images, this is what you see in the second row here, and this resulted in better predictive performance. So the unmet clinical need here was to see if baseline chest X-ray scans could provide information regarding disease progression. This was a multi-site study involving Stony Brook University and Newark Beth Israel Medical Center. We had over 300 cases from Stony Brook University and around 70 cases from Newark Beth Israel. We trained different machine learning models using these baseline chest X-ray scans, which are acquired upon presentation and confirmation of COVID-19. So what you see on the right here are two examples of images that an algorithm was trained upon. And on the bottom is the class activation maps. So essentially the hotspots here show the regions where the deep learning model focuses its attention on while making decisions. Now we can clearly see here that there are these infiltrates, these consolidating patterns here, and the algorithm tends to focus mostly on these patterns in order to learn different features. So on the test set, our sensitivity was around 90% and our specificity was around 71%. So since then, we have included other clinical features and we have improved our specificity of close to 80% now. Okay, so the next body of work that I'd like to discuss here is how we can leverage sequential imaging data. So most of the work that you'll find in literature on COVID-19 imaging, whether it is chest radiographs or CT scans, you'll mostly find that they have been focused on snapshot imaging. However, something like this actually gives us the opportunity of studying how the disease progresses over time. So since, for many of these patients, we can have sequential chest imaging scans. And what you see on the screen is a specific example of one patient who had 4 different scans taken on 4, they were non-consecutive days, but they were within a 6-day time frame. So as we can clearly see here, in the first day, we do see some infiltrates which have clearly increased on the second day. And on the third day, it has sort of traversed throughout the, both the lungs. And then after a few days, the infiltrates resolve and we see that the lungs are clearing up. Now, the goal here is to see how the imaging features, the progression of the imaging features can be studied to build better outcome prediction models. So for this particular study, we had chest X-rays from about 93 patients, and altogether there were 620 scans. Now, each of these scans were assigned a severity score of 0, 1, or 2, depending on the level of lung infiltrates by our collaborating radiologists. So 0 would mean that it was mostly clear. 1 would mean that there were some infiltrates, and 2 would mean that there was quite a high level of lung infiltrates. So here's an example of 4 different patients, and what you see on the top left corner, this was a patient who did not require mechanical ventilation and recovered. B was a patient who required mechanical ventilation and recovered. And the cases in the second row, there are examples of patients who required mechanical ventilation and eventually passed away. So we wanted to see if we could actually use the infiltrate scores, and not just that, we also wanted to use radiomics and deep learning algorithms to see if we can extract subtle imaging cues that would help us predict eventual outcome better. So here's our proposed framework. So we had input images from multiple different time points, and we divided the lungs into 3 different zones, both the left lung and the right lung. And the severity scores were provided by the radiologists. And then we had a convolutional neural network, LSTM block. So the CNN block essentially learns or extracts the imaging features from the different regions here. And then the LSTM block, it's essentially a memory unit. It learns how the features sort of progress from day 1 to day 2 and so forth. So the goal here was to use the first few time point of imaging and then predict what will happen on the, let's say, the 10th day or the 15th day. And by prediction, I mean we wanted to figure out, or we wanted to develop a model that would predict the actual severity scores of the different lung zones. So using this model, we also had a transfer learning based baseline approach. It was a simple VGG16 architecture, which was used as a feature extractor. And then we used that in conjunction with a simple 1D neural network to predict the output. So these are our results. So we have 2 different baselines, 2 different variants. So the variants that we considered here were either removing the LSTM block or the CNN block, and then using the different approaches, we found that ours was significantly better than most of the approaches here for the different lung zones. So here we show results for left lung upper, middle, lower, and similarly for the right lung zones as well. So coming to the next piece of work that I'd like to discuss here. So what we wanted to do in our model was to leverage the domain of this particular problem. So essentially, there is a certain way in which the diseases or the infiltrates progress in a lung zone. And again, this can vary from one patient to another, but broadly speaking, you find these infiltrates sort of progressing from the lower lung zone to the upper lung zone. More importantly, when you divide the lung into 3 different zones or 6 different zones rather, there is an obvious similarity of features between adjacent zones as compared to the faraway zones. For example, if you consider imaging features from the middle zone here, that would exhibit higher similarity or correlation between features in the upper zone or the lower zone as compared to features that you would take from the upper zone and the lower zone and then look at their similarity. So we wanted to model this, this domain information into our deep learning frameworks. So just to summarize, the disease patterns in adjacent regions tend to be more spatially related to each other as compared to disease patterns from faraway regions. So here's a modification of what I showed in a couple slides ago. So in addition to having a CNN LSTM framework, we also had a dedicated correlation module. Now this correlation module would essentially maximize the correlation between features coming from adjacent regions, and it would minimize the correlation of features coming from further away regions. Now this sort of makes clinical intuition, it makes clinical sense because this is exactly how these infiltrates progress. Now, using this particular approach, we could actually improve upon our previous results. And as you can see here, for the left lung upper and the right lung upper, we could achieve an accuracy of close to 75%. It was about a 3-point increase in accuracy as compared to the previous method, which did not explicitly account for the correlation or the similarity of features between the different lung zones. So now the final piece of work that I'd like to talk about here is a generative approach. And here we were inspired by the observation that in the disease course of an individual patient, the in-lung texture pattern, it changes notably while the lung structure remains almost the same. Now, this is not just true for COVID, but this is actually true for many other pulmonary diseases. So we assume that the in-lung texture conveys important messages about lung diseases and the outcome. And for example, so you see one patient here where on day 2, you have the infiltrate levels, which is not high. And then day 23, you see quite a lot of infiltrates in that patient. And this is essentially just a zoomed in version of what the texture of the lung would look like. You can see it's sort of a more homogeneous pattern, while here it is very heterogeneous. You can see there's a cotton wool kind of appearance in this patch right here. However, when you look at the texture, when you look at the structure of the different lungs on the 2 different days, you can see that the structure is very similar. In fact, it's exactly similar. So there wasn't much change in the structure of the lungs, but you could see the texture changing significantly. Now, so what this tells us is the texture is what is implicated in the final, progression or the outcome of this particular disease. So essentially, the in-lung texture is reflective of the disease severity, and we wanted to see if we can build, machine learning or deep learning models that could characterize the changes in texture and while maintaining the constant structure. So we developed something that we call the lung swapping autoencoder. Now, this is a representation learning approach. So what this essentially does is, so let's say we have 2 different lungs, image 1 and image 2. So this is one lung and this is another lung. They have different textures and they have different structures. Now, in this particular model, we would retain the. So let's say we want to synthesize a new image that has the texture of the first lung and the structure of the second lung. So, okay, so I see that there are a few questions coming up. I'll most likely take these questions at the end. Yeah. So, so in this particular problem, we wanted to synthesize new images by retaining the texture of some lung and the structure of other lungs. And essentially, this is a generative approach. So we had a distortion suppression by a patch contrastive loss, and we essentially suppressed the out of lung textures and retained the in lung textures. So here's a slide that will give you a clear idea of what exactly we are trying to do. So let's say we have image 1 and image 2. And we are taking the structure of image 1 and the texture of image 2. And we are generating this hybrid image that you see here. Now, as you can clearly see in this hybrid image, we have successfully removed the texture of the COVID infiltrate patterns from image 1. So these are the COVID infiltrate patterns here and here. And if we take the texture of lung 2, you can see that the patterns have been removed, but we still retain the structure of image 1 right here. So we can also do the converse. We can take the structure of image 2 and we can take the texture from image 1. Now, if you closely look at, if you observe this image right here, we can see that the structure of image 2 has been retained in this particular image, and we have been able to successfully introduce these COVID textures into this particular image right here. And this is sort of a mashup of image 1 and image 2 from both the structural and the textural perspective. Now, the most logical question here is, how will this even help in any medical imaging application? Now, I mean, yes, we have a lot of images that we can train our models on, but let's say in the initial portion of the pandemic, when we did not have that many images that we could train our models on, we could use something like this and use publicly available, let's say, healthy lung data and limited COVID data to actually generate or synthesize new images, which we could then use for machine learning applications. Additionally, what we also saw was when we augmented our data set with these hybrid images, we could actually improve outcome prediction. And I'll show some of those results in the next few slides. So the first task here was to classify different pulmonary diseases. So after the lung swapping autoencoder was trained, we applied to perform 2 downstream tasks. The first was to see if the texture encoder in the swapping autoencoder could do or could perform or how well it could perform in classifying different pulmonary diseases on a large-scale chest X-ray 14 data set. Now, this data set has close to 100,000 or 112,000 images, and there are different images here. We have different conditions here. We have infiltration, we have atelectasis, we have cardiomegaly, we have pneumonia, and so on and so forth. So we essentially looked or tried to build models that could predict each of these different, 14 different conditions that are present in this particular data set. Now, one of the standard models, Inception V3, that performed the best. It was around 80% accurate. Ours was very close. It was around 79% accurate. However, what was more interesting was we could achieve a similar level of performance with a very small number of parameters as compared to the other heavy models that are out there. Second, we wanted to see how well this model could do in predicting outcome on our data, on Stony Brook data set. And we also included in this data set some cases from Rutgers as well. So compared to a naive swapping autoencoder, our model achieved superior performance, which indeed demonstrates that better disentanglement leads to more performance improvement. So as we can see here, the balanced error rate for a naive swapping autoencoder was about 18%. For us, it was lower, it was 16%. And the AUC increased from 86% in Inception V3, which is a standard model, to 89% in swapping autoencoder, and close to 90.5% for our lung swapping autoencoder, which was adapted for this particular purpose. So finally, we propose a data augmentation strategy, like I discussed, based on this lung swapping autoencoder. So for each chest X-ray scan, which was labeled as Y in the COVOG dataset, we can generate K hybrid images by mixing the texture with K different structure templates. So essentially, you can have one image that has a particular texture, and then you can get in as many images as you want, let's say healthy lungs with a particular structure, and we would be able to generate that many number of diseased lungs that we could then use to train our models on. So using this, our just with a 2 times augmentation, we could increase the performance of our outcome classification to 92% from the previous 90.5. And here's an example of what the deep learning model actually, or where the deep learning model learns its features from. Now, on the top, the 3 rows, you see examples of correctly classified cases. The red arrows are essentially where the infiltrate deposition is. And we can see for the most part, our algorithm can pick sort of the approximate region of the infiltrates. There are there are cases of clear misclassifications where our algorithm tends to learn from regions which are not COVID related. But we can see that how a deep learning algorithm can actually focus its attention on these disease regions on this particular slide. So the next steps, I'd just like to give a snapshot of what we are working on. So we are essentially working on integrating imaging data with clinical data. So here's a retrospective study that we did at Rutgers. So essentially, these were patients who were proned. And so we collected data before prone ventilation and after proning as well. And we collected, obviously, the standard blood gas measurements, ventilatory parameters. But in addition to that, we also collected the chest imaging data from these cases. And the top row here shows, chest X-rays of a given patient for a sustained improvement in PF ratio. This was before proning. This was 1 day after proning, and this was a few days after proning. And for the second row, we see an example of a patient where the PF ratio worsened, and we can see that similarly the infiltrates also keep getting higher and higher in this particular case. So this just shows an example of how we can use imaging data and clinical data in a combined manner to build better models of eventual outcome. So the other things that we are focusing on right now and that we would like to work on is see how these different models that we have developed can help us understand long COVID, and if they can help us predict what sort of changes these patients might have 3 months, 4 months, or 6 months down the line. So a huge shout out to all my students, my collaborators at Stony Brook, and other collaborators as well. So yeah, happy to take any questions. So the only thing that I'd like to say here is most of these techniques that we have developed, they're domain agnostic, they're disease agnostic, and we can actually apply many of these pipelines to other different applications, not just COVID or pneumonia-related applications, but also cancer-related applications, something that we are studying right now as well.
Great, thanks, Prateek. So we have some questions for Mary Saltz.
Mm-hmm.
How would lung structure ever change accepting the development of pleural effusion or pneumothorax or atelectasis? So
that's a great question, Mary. So in fact, we did observe that in certain pathologies, lung structure did change, and when that happened, our model obviously did not work well because our model was focused on picking the texture of the images rather than structure. So yes, a lung structure can change, and if it does change, then that's not something this model is equipped to handle.
So, and then how does this AI approach compare to radiologist readings, increasing infiltrates, clear lungs, et cetera?
Yeah, so we actually just got this paper published, and one of the comparative methods that we used was taking the radiologist scores and implementing them or integrating them into a simple logistic regression model. And we saw that our model was significantly better as compared to the radiologist scores. But interestingly, when we included the radiologist scores in our model, it even became better.
Okay. So Ali Aga, can you briefly describe specific histogram adjustment processes you used?
Yeah, so for this particular project, what we did was we first applied our lung segmentation algorithm. So we found out essentially the region of the lung, and then we had histograms of, so let's say a template histogram that came from a Stony Brook distribution, and then we aligned the PDF of the Rutgers dataset to our Stony Brook distribution to make to match the histogram. So that's what we did. It was a very simple technique. I mean, sorry, go ahead. Yeah.
Go ahead.
Yeah. So what I was saying is, what we could also do is we could do a linear piecewise histogram matching. That is something that has been shown to be very successful in other domains such as brain MRIs. But for this, a simple alignment seemed to work.
So what would you see the applicability of this, or the generalization of this to CT?
Yeah, so something that we could, from a model perspective, we could definitely use some of these texture structure disentanglement model to specifically learn what texture is on the CT scans, and then use them in conjunction with machine learning algorithms for any sort of downstream analysis. So the other possible opportunity here is if we do have multiple CTs, we can model the changes between different time points using CNN-LSTM approaches, and also transformer-based methods that we are starting to explore now to see if we can predict what the severity of the disease might be a few days from now. Yeah.
Great. And any other questions? Okay, Prateek. Well, this was great. And do we have? No. Okay, so we have next Monday, October 25th, fire and tenant model. And thanks, Prateek, and thanks everybody. And looking forward to seeing people over the course of the week. Thanks.
Thanks, everyone. Bye. Bye.
Bye-bye.